Okay, in the second part of our forces in motion unit, we're going to be talking about friction forces. So friction forces, you can kind of find them everywhere. So I have some examples down here at the bottom of this slide. We have a rock climber. You know, his ability to stay on the rocks is dependent on the friction force between his fingers and the rocks and his shoes and the rocks. Driving in cars, our wheels are in contact with the pavement, and because there is a pretty high coefficient of static friction, when the wheel turns, the car goes forward. We have a couple sliding friction examples or kinetic friction examples with some skiers. Their skis slide against the snow. You can add wax to the bottom of the skis to reduce that friction force so that you get a better glide. And also curling is a very interesting example. The whole sport is kind of built around trying to modify the friction forces, and they, broom the ice in front of the curling rock or curling stone. I'm not sure what it's called. But they try to modify the friction so that the stone will go where they want it to. Okay, so we're going to look specifically at how do you calculate friction forces if you know the two types of surfaces that are in contact, and also how hard they're being pressed together. Okay, so a really simple example of friction, actually, as I look at my hands here as I rub them together. So if you kind of lightly place your hands together and rub them, you can feel your hands just sort of start to heat up. There's friction, but if you push them together more and rub them, the harder you push them together, there's actually more friction and more heat energy that's lost due to friction when you press your hands harder together. So friction is dependent on how hard the surfaces are being pushed together, and also like what type of surfaces are in contact. So looking at a little bit more generally what friction is basically just a force that resists motion. So friction, like, look at the microscopic level, we can kind of think about it like irregularities on the surfaces that kind of like grab and catch against each other to resist motion. In reality, at like atomic level, friction is caused by electrostatic interactions between the atoms. But we are going to model friction on a more macroscopic level, and think of it as just a force that resists the motion of an object. So we're going to first look at the static friction force, and static means like stationary or not moving. So static friction is basically the resistive force that keeps an object from moving when you apply a force to it. So for lack of a better example, I have here a banana on a book. So I can push on this banana and it doesn't move unless I actually put a pretty big force on it. Well, not a huge force, but like it doesn't start moving as soon as I apply any sort of force. Okay, there's a point where I get to a force where it will start to move. So the static friction, when I'm pushing on this banana, the static friction is opposing the movement of the banana. So basically we have an applied force. Here's my model of a banana, I guess, or a box. I have an applied force, and then that Fs, or static friction force, is opposing the motion of the object. Okay, so like real life example, static friction is what allows you to beat your friends in a tug of war contest. Okay, you apply a force on the grass or on the ground, and your hands are applying a force on the rope, and static friction actually is what then pulls on the rope. Okay, you need to grip it pretty tight, right, to get a good grip and to get that static friction to a point where you can actually pull on the rope with you and your friends. So you're relying on static friction to kind of win at tug of war. So static friction is interesting because it actually it changes its force to offset the other applied forces. Okay, so static friction, again with my banana example, is going to directly, it's going to be an equal magnitude to this force that I'm applying to the banana. So if I apply a force of 10 newtons to this banana, static friction is going to be 10 newtons. Okay. If I apply a 20 Newton force to this banana, then static friction is going to offset that with a 20 Newton force. Okay, or let's say I even applied a 30 Newton force to this banana. Well, static friction is going to be 30 newtons to oppose that applied force. There comes a point, however, when I overcome that static friction and the banana moves. So when I overcome that, so let's say the maximum static force, and I just made this number up, let's say it was 35 newtons was the maximum static friction force that can be produced. Well, as soon as I apply force that's greater than that 35 newtons, then my banana will move. Okay. So the static friction force doesn't have a certain number. It's going to just oppose or offset other applied forces. It does, however, have kind of like a set maximum point of how much force it can produce. Okay, and we call that Fs max, or the maximum static friction force. Okay, so calculating the max static friction force, you actually have two things that are important. One, this coefficient of static friction. The coefficient of static friction depends on what two types of surfaces you have in contact. Okay, so like if you have, wood on wood, or you have rubber on concrete, like an example of these cars, or, skin on rock. Okay, all those, there's going to be a different mu-s value for whatever two surfaces you have in contact. The static, and it's called the coefficient of static friction. Okay, but the maximum static friction force also depends on the normal force acting on the object due to it being in contact with that surface. So basically that's a measure of like kind of how much the two surfaces are pressing against each other. So the more two surfaces are pressing against each other, the higher that maximum static friction force is. Okay, so the N stands for the normal force acting on the object due to its contact with the surface. So let's take a look at another example with the banana, I guess, to take a look at this. So let's take a look at static friction using this like lightweight gum package. It's plastic. Okay, I'm going to put it on top of this textbook, and when I tilt this, static friction is going to keep that gum wrapper on it, even though there's a force of gravity acting down this incline. It'll keep the gum wrapper or the gum container on there for a little bit. I tilted it to right about here, and then it slid down. Let's go ahead and now increase the mass of this by putting some erasers in the gum container. It was the most massive thing I had around the house that would fit in this container. Okay, and let's close it up and let's see how that changes the angle at which this begins to slide. Okay, so I'm going to tilt it. Okay, and not a lot. I don't know if that really demonstrated. I guess I could make this even heavier. Let's make this even heavier by putting a banana on top of it. Okay, and yeah, it still starts to slide pretty soon. Okay, but maybe it takes a little bit longer for it to start to slide. That was at a little bit more of an angle than it was when it was empty. Okay, now let's take a banana. Okay, and bananas, now we have two different surfaces in contact. So let's see how long it takes for the banana to start to slide. So you'll see that even though the banana has about the same mass as this with erasers, okay, you're going to have to take my word for it, but it's about the same mass. Because the two surfaces were different, and remember the type of surfaces in contact affect that mu, or the coefficient of static friction. So because there was different surfaces in contact, that force of static friction with the banana, that mu value is going to be higher because it can the two surfaces stick together better than the two slicker surfaces. Okay, so again, that slides pretty quickly, and then if we take the mass out of the gum container, I'll go ahead and take all the mass so we can have an extreme example. Okay, and this will start sliding pretty much as soon as I tilt the textbook. Okay, so that's kind of like visually what we're saying. So the type of surfaces in contact, that affects the mu, or the coefficient of friction. And then the amount of mass of the object affects how the normal force, or like how much those two surfaces are pressing against each other. Okay, so after viewing that example, let's actually take a look at another kind of like more quantitative way to calculate a maximum static friction force. In this example, we have a crate resting on a truck bed, and the crate is 250 kilograms. Okay, we know that the coefficient of static friction is 0.60. We are asked for two things. First, we need to find the maximum force of static friction, and then second, we want to find the acceleration of the truck, of this truck at which the box will begin to slide. Okay, so for A, this is a simple kind of plug in the numbers and solve type problem. We know that the maximum force of static friction is going to equal that coefficient of static friction times the normal force. Okay, well, the normal force here in this situation, okay, we have the force of gravity acting downward, and we're assuming this is a horizontal truck bed. We have no acceleration happening in the y direction, so the sum of the forces in the y equals 0, and we know that the normal force is going to equal that gravity force, the force of gravity, or the weight of the box. Okay, so that equals m times little g. So plugging in to our equation, the maximum force of static friction is going to equal 0.60 times m, which is 250, times 9.8. Okay, and then we take our calculator, we plug it in, and we get the maximum force of static friction is equal to, we round to 2 sig figs, so that would be 1,500 newtons. So, knowing that, now we can begin to solve B. So in B, we're asked, what is the acceleration of the truck at which the box will slide? Okay, well, if we look in our x direction, let's say that the truck was accelerating this way. Okay, if it's moving this way, the force of static friction is going to bring that box with it until this static friction force reaches its maximum of 1,500 newtons. Okay, so our friction force, okay, which is kind of pulling the box with this acceleration, as soon as that friction force exceeds 1,500 newtons, that's when the box will begin to slide. So we can plug into Newton's second law, and we have 1,500 newtons equals m times a. Well, we know the mass of our box is 250. Okay, so we get that when acceleration equals 6 meters per second squared, as soon as it is greater than 6 meters per second squared, that's a terrible greater than sign, that is when the box will begin to slide. So if this truck is at a stoplight and it accelerates with more than 6 meters per second squared, which it would probably not, that's a pretty high acceleration. It's like a race car. But anyway, if it did reach that, then the box would slide off
the bed of the truck, which would be a disaster.
Okay, so that's static friction. We're also going to look at kinetic friction, and specifically kinetic friction where the two surfaces are sliding against each other. So when they're moving relative to each other, okay, and the kinetic friction force is going to always act parallel to the surface, exerting it, and it's going to be at the point of contact. So it's going to be at that surface, okay. And just like static friction force, it's going to resist that motion, so it's in the opposite direction of, like, in this case with kinetic, in the opposite direction of the velocity of the object. Okay, so if we have an object that was moving to the right, the force of kinetic friction is going to be acting to the left. Okay, so I said earlier that curling is an example of this. So we have the curling stone that is moving forward, okay, and this is probably an exaggeration, right? It has a very small kinetic friction force acting on it because it is ice. However, there is a friction force present, and they're wiping the ice in front of them with these little brooms to try to alter that kinetic friction force. Okay, so the rock or the stone, again, I don't know what it's called, is sliding on the ice. If you've never seen curling, this is sliding this way, and these sweeper people are like sweeping the ice in front of it. Sorry, I do not know the actual legit terms for these people. The sweepers, we'll call them the sweepers. Kinetic friction force is always less than the maximum force of static friction. Okay, so, and that makes sense, right? Because if you have an object on an incline, and so let's look at our banana example again. So we have our object on our incline. Okay, let's say we got it to the point just before it's about to slide, and there's a 35 Newton force down. The max static friction force is up the incline at 35 newtons, but as soon as that banana begins to slide, it just continues moving. It's not like as soon as it starts moving and the kinetic friction force is more than the static friction force, it would just stop, and we'd have this repeating, like, start-stop type deal. So it makes sense that the kinetic friction force must be less, and a lot of times it's actually kind of significantly less. So like as soon as this banana starts moving, it's going to continue down the incline because the kinetic friction force is only, let's say, 14 newtons, okay? And it still has that force of gravity acting down. As soon as I tilt it past the angle that gives 35 newtons of force down the incline, as soon as it gets to 36, it's going to start sliding because its maximum static friction force was 35, okay? And then as soon as it starts sliding, now we're dealing with kinetic friction, which that mu value for kinetic friction, the mu, we're going to calculate kinetic friction in the same way, and the mu value is quite a bit less usually for kinetic friction. Okay, so in this case, if these really were our values, we would have an acceleration. Not only is it moving, it's going to accelerate, right? Because 36, this force is quite a bit bigger than 14, so we have a net force down the incline, which we know from Newton's second law is going to accelerate the object. Okay, so like I was just starting to say, we calculate kinetic friction very similarly to how we calculate static friction. We just have a different value for this, the coefficient of kinetic friction, okay, the mu k. Okay, and again, it depends on the two surfaces in contact, and then we also have the normal force that's acting on the object is important because we said the more two surfaces are pressed together, the higher the friction force. Okay, so it's kind of interesting to look at these values. So again, if you look at all of these coefficients of static friction in this column right here, they're all greater than the coefficient of kinetic friction. Okay, and it's interesting to kind of look at, well, rubber on concrete, we have a static friction force that's close to 1, kinetic friction force about 0.8, and again, these are kind of on average, right? Every situation is probably going to be slightly different, like depending on the type of rubber, or you know, the polish on a wood, or you know, so these are just average values. Don't you may see in tables values slightly different than that. Yes, I know that these are just averages. So anyway, so here's some coefficients of friction, but let's take a look at an example problem using kinetic friction.
In this example, we have a skier. Well, actually, this is a snowboarder. A snowboarder sliding down a slope that's 15 degrees with respect to horizontal. We know the coefficient of kinetic friction is 0.20, and we're asked to find what is the acceleration of the skier down the slope. Okay, so the first thing we're going to want to do is we want to draw a free body diagram of, I keep calling it a skier, it's a snowboarder. So we want to draw a free body diagram of the snowboarder. Okay, so we know that there's a force of gravity acting straight downward, right? Force of gravity acting down. Okay, we have a normal force acting on the skier right here because she's in contact with the slope. So that's the normal force. Okay, there is a kinetic friction force slowing her down, acting up the incline. And those are the forces acting on her. Okay, what we are going to want to do in order to figure out what this normal force is, we have to actually break gravity into its x and y components. So remember, we're going to set a reference frame here. Let's set this to be the positive x direction. And so parallel and down the slope is the positive x direction. Perpendicular to the slope is going to be our y direction. So that normal force is in our y direction. And in order to figure out what that is, since she's not accelerating in the y, the normal force is going to be equal to the force of gravity, that y component of that force of gravity. Okay, and we also, in order to calculate her acceleration, will need to know what this force of gravity is down the incline. So I'm just going to draw it up here. So that's our x component of the force of gravity. Okay, so this angle right here, theta is going to equal the 15 degrees. Remember, we derived this in our previous set of videos, but this is going to be 15-degree angle right there. So we know that our y component of gravity is going to be equal to the force of gravity times the cosine of 15 degrees. Okay, we can rewrite that as mass of the snowboarder times little g times cosine 15, and our component parallel to the incline is going to be fg times the sine of 15 degrees, because remember that is located right there, and we've just changed its position and moved it up so that it's acting on the center of mass of the skier. Okay, so we can redraw our free body diagram. So all of our forces are parallel or perpendicular to that incline, and we get something that looks like that. Okay, so if we sum our forces in the x direction and sum our forces in the y direction using Newton's second law, we know that's going to equal the mass of the snowboarder times the acceleration. In the y direction, there's no acceleration. Okay, she's not accelerating up off the slope or anything. So when we sum our forces in the y direction, we know they're going to equal 0. So we have n in the positive direction minus fgy, oops, we need a little y right there, equals 0. Okay, so summing our forces in our y direction basically just gives us that the normal force is going to be equal to mg cosine 15. Okay, that actually is helpful, but it's not helpful in telling us what that acceleration is. We don't have an a in that equation ever anywhere. So let's go ahead and look in our x direction. We know the sum of forces in the x direction. Well, we've called down the slope our positive direction. So we got fg sine of 15 minus force of kinetic friction equals m times a. Okay, remember Fg is just the mass of the skier times little g sine of 15. Okay, our force of kinetic friction. Okay, well, our force of friction we know is equal to the coefficient of kinetic friction times the normal force. Okay, well, we know what the normal force is, and we know what kinetic friction is. So mu k mg cosine 15. And we're not sure of the mass, but it's looking like all of these terms are going to have the mass in it. So I think we're going to be lucky that those masses are going to cancel out. Okay, so let's plug in for force of kinetic friction this. So we have minus mu k mg cosine 15 equals ma. Okay, well, indeed, all of the mass of the skier actually doesn't matter. Those cancel out. Okay, so we're left with g sine 15 minus mu k g cosine 15 equals a. And now we just end up having to plug in our numbers. So we got 9.8 times sine of 15 minus mu k was 0.20. That was given in the problem. Okay, and when we plug in and solve, we get that the acceleration is 0.64. So 0.64 meters per second squared. Okay, so the trick here was first we know that in order to solve for our force of kinetic friction, we're going to need the normal force. We were given mu k. So in order to find the normal force, we have to sum our forces in the y direction. And those are going to equal 0 because there is no acceleration in the y. Then we also can sum our forces in the x direction. That's where our acceleration in the a shows up. And we know that we have the x component of gravity acting down the incline, and we have the force of kinetic friction resisting that motion. So we can plug in what we know, and fortunately our masses all cancel. Okay, so even though we don't know the mass of this snowboarder, we can still solve for the acceleration down the incline. And we find that it's 0.64 meters per second squared.